Hi everyone, my name is Elisa. I'm from the University of Technology from Tallinn, and I'm going to talk a bit about a classification algorithm I created in the context specifically of urban material stock assessment. I mainly deal with apartment buildings, and majority of apartment buildings in Europe have been built during mass construction periods. But specifically in countries that were previously under Soviet Union rule, majority of buildings during that time were built by standardized floor plan templates or blueprints with documented material specifications, which means that all over we have really basically identical or near identical buildings. Just a few examples. This was Tallinn, but close to Tallinn we have Riga. Now looking at this picture, if I didn't see this tower there, I would honestly think these are the same neighborhoods, but no, this one is the neighboring country. And a bit further away we have, of course, for example, Ukraine example. Previously, these blueprints or templates were majorly in archives where you couldn't access them. But now we have some books that have collected these documents in university. We have put some effort into digitalizing these. So now we actually have these templates and these material specifications. Yes, they are majorly in Russian, but with today's technology, it's no longer a problem to translate at scale. Now, what we don't have is a data set that would tell us which buildings were built by which design, nor even how many designs or how many buildings there are that were built by one specific design. Just a few more examples of mass construction. So my goal was to create an algorithm to detect which building was built by which series and designs on a national scale. And then as a use case, I decided to use material stock estimation. Why most of life cycle assessments could benefit from more granular and detailed data, but I think for materials especially, having these blueprints, having these specifications would allow us to have actually not only raw material estimations, but also element estimations. So how many precast wall elements there are in what specific buildings, how many of these have the window inside the panel, to basically allow for selected deconstruction over demolition and timely recovery. So how to get elements before they deteriorate any further. So this is the workflow that I came up with. I have two main inputs. First, we have Estonian Building Registry, which in its essence is basically Estonian building logbook. So it has very general data, year of construction, areas of apartments, and so on. Then I need something to match this data with. So I created this template database that has 11 series, and 11 series we have 75 different designs that are documented. So a bit more about the templates. Basically, it is a machine-readable representation of a building. Kind of similar to an IFC, it's just a representation, but it's a really small one because my goal was to make it scalable, that I would be able to use it on a national scale, so I couldn't have many different attributes that might have been missing for some buildings and not missing for others. So we have, first of all, of course, series and series design specification. We have type of building. This matters because these blueprints, there were two types. First, there were modular blueprints, so you would have a blueprint of a staircase, and then you could configure them together to create an actual building, or there were whole buildings. So in there, of course, you have the entire building. Then for the attributes that I actually compare, we have the pattern. Now, what is a pattern? Just to showcase, if you would walk into a Soviet Union apartment building, you would have 2 to 4 apartment doors, and they are always numbered, as usual apartments are. Now these numbers aren't the numbers of the apartment itself, they are actually how many rooms does a specific apartment have and what's the order of those. And what we found is that is actually the main thing that distinguishes different designs and how you can find the specific design. So for modular buildings, of course, it's just a single regular list. For those full buildings, it's a nested list. So if we walk into this apartment building from the first staircase, the first apartment would have 2 rooms, the second one 1 room, and third one 3 rooms. Then there is the area pattern. It's not on the list because it's the for each staircase the area of all apartments summarized. And then floor number, because generally these blueprints were built by specific floor numbers. Sometimes only 1 floor number, sometimes there would be like 4 or 5, for example. So, of course, when I have these inputs, I wanted to also allow for user input, just to make it scalable for outside of Estonia. So, I know that not all countries have the similar data sets as we do, so I wanted to keep the attributes minimal and make it so that the user can input their data and try to create the match. Then if you do have this data, of course, some pre-processing is necessary. Some data is directly from the registry, some data is derived. But the major thing I do is that I compare the data on building itself as it is. For example, it would come as this list of a pattern. But I also create a mirrored version of the same thing, because while the blueprints were always numbered exactly the same, a real building might not have the same order of staircases. So it could be mirrored. And some other alignment things I do. So how do I actually find the match? I decided to go and use distant calculations instead of machine learning, what would probably be the first idea. Why that? Because we already have 75 designs. It's just way too many data points for us, we thought, to only use machine learning. So I went the distance calculation route, and for each attribute I used this different distance measurements. For example, for patterns, because there the order matters, I use Lernstein's distance, and floor numbers, the absolute distance, for example. Then when I have those 3 distances calculated, I combine them by weighing them. And then the final prediction, because we know that we don't have all the designs, we don't have all the templates, and also not all apartment buildings are built by these templates. So I needed a condition to say that, okay, this building does not have a match. And for this version of the algorithm, I just decided an absolute, if distance was more than 4, I decided that this is definitely a mismatch. And otherwise, the closest distance will be used. So a bit of results. Used almost 400 buildings to validate it. Overall accuracy for series for 60%, temporal 50%. But if I excluded the buildings that should not be classified because they don't have a match in the template, and we know that, then it raised to 80%, that's 70%. So we know that if we do have a match, it's quite trustworthy. But also the recall varies sharply by series, so some series have amazing recall and some not so much. And if you remember the first few series, then we applied this on national scale. So I took all apartment buildings in Estonia that were built between 1960s and 2000s, and I classified those. And so you can see those that have a great recall are generally those that we found the most of. Just to go quickly, we then selected one of the major series, and my coworker used these documents to create material estimation. So if generally this is what she would get, she actually was able to get how many external wall panels, internal load-bearing panels, internal panels, and floor panels there are over all these buildings that belong into this series, that belong into specific designs showcased here. So the main conclusion, I'm not going to much into it. For me, the most interesting was the distance score that was supposed to only measure distance, but in the end, for me, turned into a confidence metric. So if the distance is really small, like 0 or under 1, then it's most likely correctly classified. If it goes up, it's let's say more than 4, then it's definitely misclassified, and then in the middle, it's the muddy area. Thank you. Sorry for going a bit over time.